I welcome everyone to this video. I am Mr. Ish. Thank you for joining me. Let's look here at a specific item of a topic, generalized topic, projectile motion, which is usually a curse for many students when they're studying it because it's difficult. Here we're going to look and focus at the range. What's the maximum range of a projectile if it is shot with a given velocity at a given angle? How far does it go? Let's look at it, but we're going to be looking here in terms of a derivation perspective because that will help you understand the how and the why about it, and then it makes it easier for you. What is the gist of this topic? If you are looking here at an x and y axis and it represents the point at which the projectile is shot up, a certain projectile demonstrates that type of a path. It's shot at a particular initial velocity and this is it, at a particular angle. How can we determine the maximum extent that it went, the maximum distance? And you're focusing here at everything here along the x dimension, hence we're looking at the range with the x. That's your focus in terms of the horizontal extent of that path. And how do we understand this? Look right here. Your point of focus is actually your initial velocity. The initial velocity here is not going to be 0 because for a projectile to have achieved a certain motion, it had to be having a velocity which is not equal to 0. Otherwise, there would have been no projectile motion to begin with. Initial velocity here is not going to be equal to 0 unless you don't want to have any movement at all. Anyhow, look. I'm looking over here, initial velocity vector that you see right over here. It has a certain x and a y component and a certain right triangle develops a certain angle. Your angle here is with respect to your VO, your velocity. Your initial velocity is not with respect to the path. Of course here, if you were to do a derivative at some particular point over here, the angle would match for both the parabolic curve and your straight line over here, but only for a particular instant, after which the angle would differ. It doesn't matter because we're focusing at this angle right over here, theta, which matches the angle of your VO, your initial velocity. What can we do with this? I have this velocity initial which represents the hypotenuse of this right triangle. I have a horizontal component of velocity. I have a vertical component of my velocity, x and y. Demonstrate equations which will help you determine the x and your y, your horizontal and your vertical components, your velocity. How can I do it? If I were to do cosine of this angle theta, I'm looking at a horizontal component divided by the hypotenuse. Now these do not cancel out. You don't want to cancel out because this is just a designation. VOX is just showing you the horizontal component of your velocity. You don't want to cancel out because it will be an error to do so. Sine theta, sine regards to this theta is equal to my opposite dimension of my velocity, my vertical dimension of velocity, which is your opposite of your right triangle divided by hypotenuse. In each particular instance, solve for these x and the y components. My x component of my velocity is equal to what? It's equal to my initial velocity because you transfer these on the both side, on the other side of the equal sign and multiply times cosine theta. My y dimension, my vertical dimension of my velocity is equal to, VO, initial velocity times sine theta. We've done all of this and it's easy. But remember again, the gist of this is demonstrating the maximum range of your projectile movement, and we're looking at projectile motion. Nothing is being shot straight up or straight down. It's being shot at an angle. Hence, you're going to have a little bit more of a dimension come into play with regards to just something going up and down. Those are easy. When you have projectiles shot at an angle, it becomes a little tricky. Your initial development is of those two right there. Now think back to a famous equation you already know. S is equal to your displacement is equal to initial velocity times time plus half at squared, where your a acceleration can be interchangeable with g. You know that to be 9.8 meters per second square. Of course, this can be represented in different other units. Then obviously the 9.8 will change. You could have converted into feet per second square, but then this 9.8 will change. Anyhow, we're keeping here 9.8 meters per second square. The a and the g are interchangeable. Now, I'm using over here the a. Nothing wrong with doing that, but this represents here your displacement, but with regards to no representation, is this horizontal or vertical? You have to look here in terms of x, sx. You should be looking in terms of sy, your horizontal and your vertical components, as you have for velocity. Anyhow, now what do? Let's focus over here on the easier one, sx, your horizontal component of this. In a horizontal component, if I'm looking here at everything horizontally, you're looking exactly at a 0 degrees. That's your x, your horizontal component. Gravity does not play at all. This goes away. you're looking over here at your horizontal component of your velocity coming into play. Your horizontal component velocity is equal to what? You have a VO cosine theta. My O here represents initial. VO, initial velocity times cosine theta times that t. I'm looking here only at this part. When I'm looking at the horizontal component of my displacement, this goes away because acceleration is not coming into play because the gravity part is vertical, not horizontal. Anyhow, now I have to look here at the vertical component. It's easy. Now everything comes into play, but then you're focusing over here. Your vertical component velocity was what? It was VO, initial velocity sine theta. This initial velocity cosine theta, initial velocity sine theta is coming only for this part right here, the VO. Then the time is still being attached to it by product minus half at square. Why is it minus half at square? If I have a velocity in a vertical dimension, it is always being counteracted by gravity in the opposing direction. The velocity going upwards, VOY, but it is counteracted by your acceleration down, and you could put a minus because it's opposite direction. Hence, you're going to see a minus at square. The minus of your acceleration vector will affect that positive sign and convert it to minus. As you see, vectors can be reversed in terms of direction by means of a negative. This right here represents what you need to know. I have now 4 equations. I have this, I have this, and I have this, Sx and xy. What do I do with this? Focus right over here at this. Your vertical component of your displacement. Again, when we're talking about projectile motion, the maximum range, we're looking at the horizontal component. You're focusing here at this, your horizontal component. We're not looking here at maximum height, we're looking at maximum range. How far did the projectile go? Where did it land? With regards to arriving at this, you need to examine this Sy first. Why do you examine it? Because when you look here at what the Sy is equal to, it's equal to a quadratic equation. Look, I have an initial velocity sine theta times t minus half at square. I can isolate a time. Assume it's equal to 0. Isolate the time. You are looking at VO, initial velocity sine theta minus half at is equal to 0. Solve for t. In one instance, t is equal to 0 because it's equal to, you have 2 factors here. T is equal to 0, but then you have this. You have to solve this for t. You push this component on the other side, you'll have a minus VO sine theta. Then you push the minus half a on the other side. The 2 will multiply because it's a denominator here, it multiplies on the other side. Then you have a minus a. When you, this is obviously equal to t because here in this equation, in this factor, you have 2 factors. In this factor, you're solving for t. This thing goes away. You're going to have t is equal to what? 2 VO, your initial velocity sine theta over acceleration. And this here is equal to t. How can you represent this graphically? I'll erase this because I was just looking at the quadratic equation arising from your Sy and I'm solving here for t. If you were to graph this out on an x and y axis, you're looking at 2 x-intercepts. And the beauty of it is this. It's nothing other than just a parabola. Here's 1. If you were to look at this t is equal to 0, this one right here is 1 factor, this here is the other factor. You put these values in your original and you'll have 1 is 0, 0. The other one item will be this. This right here is my x-axis with time. This right here is 1. You have your parabolic curve. Here is your other one, which will represent this particular time. At this particular time, you'll have your maximum displacement, your range you're looking at. But we have to determine it. We're almost there, but we're not there yet. We have arrived at a most important item and we will use it. So, how do we use that item? I've determined time here is equal to 2 VO sine theta a and 0. It's no point in using this particular factor value for x because it's going to leave me to 0, 0 where the motion has not started. I need to use this particular factor because this is where the motion has ended. At that particular time, the experiment came to an end. But at that particular time, you'll have your maximum range, and that's what we are interested in. I will take this item here for time, and I'll plug it right here, and focus on my equation, which will give me what I want to know. My projectile motion maximum range, Sx. You'll put that value, your factor t, right over here. I'll have this Sx here is equal to initial velocity, cosine theta times my t, by this factor I've determined it, 2 times VO, sine theta over acceleration, and compute this. You have 2 velocities initials which will become velocity initial square. I have a 2 cosine theta sine theta. Think about your trigonometric identities. I have 2 sine theta cosine theta. which is no different than sine 2 theta. It's a double angle formula. Sine 2 theta is equal to 2 sine theta cosine theta. I'm looking at that here. Cosine theta times 2 times sine theta. I have a 2 sine theta cosine theta, but I'm going to use sine 2 theta because it is indeed equal to that. It's fewer number of terms and it's better. I have a sine 2 theta, and then I have this acceleration in my denominator, and this right here is your equation. If you ever want to look here at a particular projectile which has been shot at a particular angle with a velocity that is not zero, an initial velocity that's not equal to zero, the maximum extent, the range where it will land in the displacement will be measured by this equation you see over here, and it will be correct. I'll post it for you right here. I'm removing this item here because you don't need to see it. What I'm most interested in here was my maximum range, and we have derived that equation, and it's equal to this. Initial velocity squared times sine 2 theta over my acceleration or gravity. Either is interchangeable. Let's close out here with two examples and we're done. I have two items which are thrown, two projectiles. Question A, question B. Let's look here at question A first. A projectile is shot at an initial velocity of 100 meters per second at an angle of 60 degrees with regards to your horizontal. What is the maximum range it will extend up to? Where would it land? Look, this is what we have. You're looking here at its angle which is 60 degrees. Your initial velocity here is equal to 100. Where did it land? Obviously it's going to be a parabolic motion. It's going to be over here. Where is this in terms of your displacement? We need to determine it. You have your formula. Your formula is initial velocity squared times sine of 2 theta over acceleration, where acceleration is your acceleration due to gravity. Plug everything in. Plug these items. I have a sine of 2 theta. My angle here is 60, but 2 theta is 120. I have 120 sine times my initial velocity 100 squared divided by 9.8 for gravity. I'm getting here 883.7, and that will be your answer, 883.7 meters. It will land 883.7 meters away from its original starting point. You can say it towards the right. There's nothing wrong with saying that. 883.7 meters to the right. Now that answer is correct and that question has been solved. Let's look here at the next one. A projectile is shot at 30 degrees with respect to your horizontal or your ground with an initial velocity of 250 meters. Where is it going to land with respect to its origination point? How far is the range of that motion? You'll put everything in here. I have 2 theta here. I'm looking at theta here which is 30, but 2 theta is 2 times 30 which is 60. 60 sine times my initial velocity which is 250 squared divided by 9.8 gravity, 5,523. I have over here 5,523, and I won't put any decimal places, meters, and it will be correct, and we've done it. If someone were to ask you how can you determine the maximum range of a projectile in terms of a motion, where it landed, your formula is this. The range is always equal to, in terms of the horizontal dimension, initial velocity squared times sine 2 theta, your angle with respect to your horizontal, divided by acceleration, A or G. Either or, it doesn't matter. Both of these answers are correct. Thank you for watching.